So in this lecture, I will give another proof that the Lebesgue measure is a sigma additive. So if you are happy with the previous proof, you can skip this lecture. It's not important for the next lectures, but I would like to mention this proof, which is based on some other topology property of the real numbers. So my goal is the following. So we have defined a function mu, which is defined in the algebra generated by the intervals, which takes value in R plus extended, and we want to prove that, so my main result of this lecture is that mu is sigma additive on A. But remember, so we have the semi-algebra formed by the intervals AB and the semi-infinite intervals A plus infinity minus infinity B, and then the empty set and the set R. So I'm calling S the semi-algebra formed by these sets, A the algebra generated by this semi-algebra S, and we want to prove that mu is sigma additive on A, where, remember, mu is the unique extension of the set function which is defined on S by giving to the interval AB, so mu of AB is equal to B minus A. And it's plus infinity in these three cases and equal to 0. So we extended this measure to the algebra, and now I want to show that this set function is sigma additive on this algebra. And the proof is based on a previous result, which tells us that if we want to show that mu is sigma additive on A, well, if we restrict mu to an interval, say, minus n, so let's restrict mu to minus n, we have now a measure which is finite on this interval, and in order to prove that mu is sigma additive in this interval, well, it's enough to prove that mu is continuous from above at the empty set. And this is what we want to prove, is that mu is continuous from above at the empty set, which means that we have to show that if I have a sequence of sets ek, which is decreasing to the empty set, all ek's contained in minus n, that this implies that mu of ek is converging to 0. This is what we will prove. We will prove that if we have any sequence which is decreasing to the empty set, sequence of sets contained in minus n, then mu of ek converges to 0. So this is the goal of this lecture today. So what we want to prove is that if we have a sequence ek, which is decreasing to the empty set, ek elements of my algebra A, and in such a way that the intersection, so it's empty, and mu, we want to prove that this implies that mu k converge to 0. Right? And I'm assuming here also that all these sets ek are contained in minus n. Right? So what I want to prove is that if I have a sequence ek, which is decreasing to the empty set, whose sets are all members of my algebra A, and they are all contained in the interval minus n, then mu of ek converge to 0. And the way in which we will prove this statement is that, well, we will assume that this is not true, and we will find a contradiction. So what does it mean to assume that this expression is not true? Well, it means that there exists a sequence ek decreasing to the empty set for which mu of ek is not converging to 0. So we will assume that there exists a sequence ek decreasing to the empty set, ek in the algebra, ek contained in minus n, and we will suppose that mu of ek does not converge to 0, and since it's decreasing, this means that mu of ek, it's bounded below by a strictly positive constant. Let's call this strictly positive constant 2 delta. So I will assume that mu of ek, it's greater or equal than 2 delta. And from that, we will find a contradiction. And what is the contradiction? Well, starting from this sequence ek, we will find a sequence gk of compact sets so they will be compact. They will be decreasing, so gk will contain gk plus 1, and they will be all non-empty, and they will be contained in ek. And I claim that this is a contradiction because if gk is contained in ek, this implies that the intersection of gk, it's contained in the intersection of ek, but the intersection of ek is empty. So this set is empty. And therefore, I have a sequence of compact sets which are decreasing and whose intersection is empty. So we know from topology that in this case, all sets gk are empty starting from some index k naught. But here, the sets gk will be non-empty. So this is a contradiction. It's not possible to have a decreasing set of compact sets whose intersection is empty and whose sets are not empty for all k. So this is the way in which we will find our contradiction. So let me just remind, ek are elements of the algebra, they are decreasing to the empty set, and I'm assuming that they have a strictly positive measure. And now I will construct from this sequence a new sequence of compact sets. Well, we will do that by induction. So let me start with step 1, which is the construction of the set G1, if you want. Well, I know that ek E1, so let me consider the set E1. E1, it's an element of the algebra. So I know that E1 can be written as a finite disjoint union from 1 to n1 of elements of my semi-algebra. Since E1 it's contained in the interval minus nn, these intervals are all finite intervals, so they can be written as A1j, B1j. I know that there exist these intervals, a finite number of such intervals, and E1 it's given by this union. So from E1 I will construct F1. So how is F1? Well, I'll just consider a positive epsilon, and I will add to A1j this epsilon 1. And I will choose epsilon 1 small enough for A1j plus epsilon 1 to be smaller than B1j. I can always do that because A1 it's smaller than B1j. And then my first observation is that F1 it's an element of the algebra. My second observation is that F1 it's contained in the closure of F1. And if I choose epsilon 1 strictly positive, this closure of F1 it's contained on E1. Okay. The set G1, which I alluded to before, it will be given by this F1 bar. So this is my first compact set G1. And now I have the following observation. Well, I can choose here epsilon 1, it's anything which is sufficiently small and positive. Well, I will choose epsilon 1 in such a way that the measure of the set E1 minus the set F1 to be smaller than delta over 2. Okay? So F1 it's an element of my algebra. E1 it's an element of my algebra. So E1 minus F1 it's also an element of my algebra, and therefore mu of this set it's well defined. And now I can choose epsilon 1 small enough for this difference to be smaller than delta over 2. Okay? So, and this is my first step. So I constructed a set F1. So let me just summarize what we did here. I construct my set F1, which is contained in its closure, which is a compact set, which is itself contained in E1, and mu of E1 minus F1, it's smaller or equal than delta over 2. Well, this number delta, remember, it's the one which appears in the definition of the sequence EK. So this is the conclusion of my first step. Now I will start from that and construct a set F2. And this is the step, my second step. And my second step, I will construct the set G2, and then I will use an induction argument in order to construct the set Gn plus 1 from the set Gn. So I just remind you what we did in step 1. Step 1, we construct a set F1, which is contained in the closure, which is contained in E1. And this set F1 was chosen in such a way that the measure of E1 minus F1 is less or equal than delta over 2. And here I just remember that EK is a sequence which is decreasing, but whose measure it's always bounded above by 2 delta. So now, in step 2, I want to construct my set G2. And this is how it goes. Well, my first claim is that I can obtain a lower bound on this measure of the set E2 intersection F1. So remember, F1 it's an element of my algebra, E2 also, so this intersection it's an element of my algebra. And what I claim is that I can get an upper bound for that, for the measure of that set due to these two bounds. Let's see how I prove. Well, that's easy. Let's start with the set E2. E2, I can rewrite its measure as the measure of E2 intersection F1 plus the measure of E2 minus the set F1. I'm just decomposing E2 according to F1 and the complement of F1. And now I will remember that the set EK is decreasing, which means that E2 it's contained in E1, so that the measure of this set it's less or equal than the measure of E1 minus F1. And by assumption, in my first step, the measure of E1 minus F1 it's less or equal than delta over 2. On the other hand, mu of E2, by assumption, it's bounded below by 2 delta. And therefore, from this inequality, I conclude that the measure of E2 intersection F1 is greater or equal than 2 delta minus delta over 2. And this is strictly positive. Therefore, this set is non-empty because it has a measure which is strictly positive. And what I will do now is to repeat the argument of step 1 to obtain a set F2 which is contained in this set and which is almost equal to that set. So what do I mean here? E2 intersection F1, it's an element of my algebra. So E2 intersection F1, being an element of my algebra, it can be written as the sum of j from 1 up to some index n2 of intervals of the form a to j, b to j. Okay. F1 it's an element of the algebra, E2 also, the intersection it's an element of the algebra, and in my algebra I know that all elements can be written as such unions, and since E2 is contained in minus n, all these intervals are finite intervals, so I have this expression for this set. And now what I will do, well, I will define F2 as I define F1. So I will define F2 by adding epsilon to the left endpoint So here's my definition of my set F2. From that definition, I have immediately that F2, it's contained in the closure of F2, and the closure of F2 is if I choose epsilon 2 strictly positive, well, it's contained in E1, E2 intersection F1. All right? If I choose epsilon 2 strictly positive, this set F2, the closure of this set, it's contained in that set. Well, what do I conclude from these relations? I conclude first that F2 is contained in F1. Actually, and that so let me write that, maybe with some other color. So I conclude from that F2 it's contained in F1. So I'm starting to get a decreasing family of sets. And also that the closure of F2 it's contained in E2. Okay. So I'm extending these relations. Now I have that F2, which is contained in the closure of F2, it's contained in E2. And also I have a further relation that, well, this sequence of sets is decreasing, and since it's decreasing, if I take the closure, I have the same relation, that the closure of F2 is contained in the closure of F1, and these are my compact sets, G1 and G2. So I'm starting to construct this decreasing family of compact sets, which are all contained in the sets E2. But I also need to prove an upper bound for E2 minus F2. So let's do that. So let me erase this argument here, which I'm not using anymore. And let's observe that if I choose epsilon 2 very, very small, I can make the measure of this set as close as I want from E2 minus F1. So in other words, I can choose an epsilon 2 such that the measure of E2 intersection F1 minus F2, and here I will take, I can choose it as small as I want, so I'll choose it smaller than delta over 4. Okay? And now I can obtain a bound for E2 minus F2. Yeah, I started from a bound of the measure of E1 minus F1, so in my induction argument I want to prove a bound on the measure of E2 minus F2. I want this to be small, and in order to estimate this measure, what I will do, I'll take the intersection of E2 with F1 and with the complement of F1. So this is bounded, or this is equally actually, this is equal to the measure of E2 intersection F1 minus F2 plus the measure of E2 minus F1 minus F2. Okay, just replaced E2 by the union of E2 intersection F1 and E2 intersection the complement of F1. Right? Now, by construction, this first set has measure bounded by delta over 4. And now, for the second set, I can just ignore, so what I'm claiming is that the measure of this set, it's bounded by the measure of E2 minus F1, right? Because here I'm subtracting F2 from that set, so this set here, it's contained in that set, so its measure is less or equal than the measure of that set. And now recall that EK, it's a decreasing family of sets, therefore E2 is contained in E1, so the measure of this set is bounded by the measure of E1 minus F1. And now I can use my induction argument. I already proved that the measure of E1 minus F1, it's bounded by delta over 2. So this second term here has a measure which is bounded by delta over 2. And my conclusion is that, well, the measure of E2 minus F2, it's bounded by delta over 4 plus delta over 2. So let me summarize what we did in this second step. So in step 2, we construct a set F2 such that F2, it's contained in F2 bar, which is contained in E2. F2, it's contained also in F1, right? So these are what I wrote previously. And now we have a further estimate, is that mu of E2 minus F2, it's bounded by delta over 2 plus delta over 4. Okay. So what I will do, so I extended the relations obtained in step 1 to step 2, in which I introduced a new set. So now, what remains to be done? Well, I will assume that I construct a family of sets Fk, k going from 1 up to n, with the following property. Well, I just extend this property, so I will require Fk, the closure of Fk to be contained in Ek. This for 1 between k between 1 and n. I will assume that Fk plus 1, it's contained in Fk for k between 1 and n minus 1. And I will assume that the measure of Ek, well, actually I need only the last one, En minus Fn, to be less or equal than delta over 2 plus delta over 4 plus delta over 2 to the power n. So I will assume that I constructed these sets up to n, a level n. We did it here at level n equal to 2. And I will construct a set Fn plus 1, which has all these properties, in order to use an induction argument to say that in fact we have constructed a countable family of sets satisfying these assumptions for each n. So now let's complete the induction argument. So here I wrote the hypotheses which are satisfied by the set Ek, and here what we prove up to this point. So we have this sequence of sets Fk. We know that the closure of Fk is contained in Ek for all sets Ek for all k from 1 to n. This is a decreasing sequence of sets, and we also know that the measure of En minus Fn is bounded by this quantity, and my goal now is to construct my set Fn plus 1. So this is the goal, and the argument I will use, it's the argument I used in step 1 and step 2. I'm first, claiming that we can get a lower bound for the measure of En plus 1 intersection Fn, because I want this set Fn plus 1 to be contained in that set, to be non-empty. So I have to show that this set is non-empty, and to prove that this set is non-empty, I'll get a lower bound on the measure of this set. And so what did we do? Well, we considered the set En plus 1. We know by assumption that the measure of this set is bounded below by 2 delta. On the other hand, if I intersect this set with Fn, I get that the measure of this set is equal to En plus 1 intersection Fn plus mu of En plus 1 minus Fn. But now we use the fact that the sequence Ek is decreasing to bound this measure by the measure of En minus Fn, and by assumption the measure of En minus Fn it's bounded by the sum, therefore it's bounded by delta, and therefore the measure of En plus 1 intersection Fn, it's larger or equal than 2 delta minus delta, so it's larger than delta, which is strictly positive. Okay, so this is the same argument we used in step 1 and step 2. So we get this bound. Now, once that we have that bound, we can argue that this is a non-empty set, which is an element of the algebra, because En plus 1 and Fn are elements of the algebra, and they are contained in this interval minus n, which means that En plus 1 intersection Fn can be written as the joint union from j from 1 up to kn maybe plus 1 of intervals of type En plus 1 j Bn plus 1 j. Okay? Since this set it's an element of the algebra, it can be written as such a union. And then what did we do? Well, we defined Fn plus 1 to be the same sum, but now adding some epsilon to An, to the left endpoint. Okay. So this is the definition of Fn plus 1, and I will take epsilon n plus 1 strictly positive, if fn plus 1, well, and small enough for this interval to be, there are a finite number of intervals, so we can take epsilon n plus 1, small enough for these intervals to be all non-empty. So by choosing epsilon plus 1 strictly positive, what we immediately get is that fn plus 1, it's contained in the closure of fn plus 1, and the closure of fn plus 1, it's contained in en plus 1 intersection fn. Okay. Which means that fn plus 1, it's contained in en plus 1, and actually the closure of fn plus 1 is contained in en plus 1, and fn plus 1, it's contained in fn. Okay. So these are, this extends these first two conditions to n plus 1. Right? We just proved that the closure of fn plus 1 is contained in en plus 1, so it extends this relation to n plus 1, and that fn plus 1 is contained in fn. This extends this relation to k equal to n. So now it remains to show that the measure of en plus 1 minus fn plus 1, it's bounded by such an expression. And this is very simple, because now here is fn plus 1. I can choose epsilon n plus 1 to be very, very, very small for the measure of en plus 1, which is this set, intersection fn minus fn plus 1. I want this measure to be very, very small. How small? Well, bounded by delta over 2n plus 1. And this can be achieved just by making epsilon n plus 1 very, very small. So once we have that, it's easy to extend this bound to n plus 1. And this is what we will do now. So I don't need any more these formula. I'll just erase them to conclude the argument. Well, the argument, well, we've seen it in step 2. I want to bound this expression. So I know that this expression is bounded by delta over 2n plus 1, and I want a bound for en plus 1 minus fn plus 1. So I need an upper bound for the measure of that set. And what was the argument? Well, let's decompose en plus 1 according to fn and the complement of fn. So I will write this as the measure of en plus 1 intersection fn minus fn plus 1 plus the measure of en plus 1 minus fn minus fn plus 1. Well, from that bound, we obtain that this expression here, which is exactly that one, so the first term, it's bounded by delta divided by 2 to the power n plus 1. On the other hand, this set here, it's contained in that set. So the measure of this set, it's less or equal than the measure of en plus 1 minus fn. And since the family ek is decreasing, en plus 1 is contained in en. So this, the measure of this set, it's less or equal than the measure of en minus fn. And by the induction assumption, the measure of this set is bounded by delta over 2 plus delta divided by 2 to the power n. therefore, we just proved that the measure of this set is bounded by this sum plus that term, which means that we just proved that the measure of this set is bounded by delta over 2 plus delta over 2n, which is the second term, plus the first term, which is delta, divided by 2n plus 1. And this is exactly what we wanted, because this inequality extends that condition to n plus 1. So this is the conclusion of this induction argument, is that we can obtain a family Fn which satisfies these conditions for all n, right? So what we just proved is that there exists, we just construct a family of sets Fn, n larger or equal to 1, which satisfy these three conditions. Okay? So now, if you recall what was the strategy, let me call Gk the closure of the set Fk. So by the second condition, we have that Gk plus 1, which is equal to Fk plus 1 closure. By this relation, this is contained in Fk, the closure of Fk, which is Gk. So this sequence Gk is decreasing. The second condition is that Gk, it's compact. Right? Because, well, we are defining, maybe let me just remind here, Gk will be Fk, the closure of Fk. So these are bounded closed sets, so they are compact. So Gk, it's a compact set. They are decreasing. Now, I claim that they are non-empty. Why they are non-empty? Well, it follows from that condition and this condition. We have that mu of En, or Ek, if you wish. Well, this is equal to mu of Ek minus Fk plus mu of Ek intersection Fk. Fk, it's contained in K, so this is mu of Ek. Mu of Ek minus Fk, it's bounded by delta. So this term, it's bounded by delta. And mu of Ek, it's bounded below by 2 delta. So from, here's Fk, right? Ek intersection Fk, since Fk, it's bounded by Ek. The intersection is equal to Fk, so here it's Fk. So we have that mu of Fk, it's larger or equal than 2 delta. And this implies, of course, that Fk, it's non-empty, and therefore Gk, or which is the closure of Fk, it's non-empty. But finally, the intersection of Gk well, since Gk is contained in Ek, the intersection of Gk, it's contained in the intersection of Ek. and the intersection of ik, it's empty. And this is a contradiction, right? We know that if we have a decreasing family of compact sets, which are all non-empty, then their intersection is non-empty. Well, but here the intersection is empty, so this is a contradiction, and this proves that the Lebesgue measure, it's sigma additive on the algebra because it is monotone, it's continuous from above at the empty set. And this concludes this lecture.